This lecture will look at software security. The key focus will be on defining some best practices, but not to dwell on current systems, but to look towards the future of secure software. And that will especially look at the .NET framework, which gives us one of the best role models for the future. Along with this, we'll look at keeping code secure, obfuscation, software security, the .NET model, and ASP.NET, and hopefully we'll be able to complete with a possible roadmap for the future. Okay, so why is it so complex, and why is software typically so insecure? Well, unfortunately, applications tend to be written in isolation from other applications and divorced from any operating system, any domain controller, any file systems, and so on. But unfortunately, applications build on top of operating systems or frameworks. They then link to services either through workgroups, which again run on operating systems, or through a network operating system. The network operating system itself provides file systems, distributed data storage, authentication infrastructures, and domains, all through different types of communication protocols such as HTTP for our applications, at the transport TCP, and at the network layer IP. So we can see here that the major problem is how to make sure that all of this is integrated and secure. So what has been the problem, and why is it that applications are so often insecure? Well, an obvious method is that there is a general lack of education in secure methods. Along with this, there's generally a lack of integration with operating systems, and the applications are typically written in isolation of the operating system. But it's the operating system itself that typically defines the security of the application itself. There is typically also a lack of testing, a lack of evaluation. Developers will often test with certain features turned off, and they can often forget that these features have been compromised in some way and then can be released. There's also a lack of understanding of protection of intellectual property. If a company has invested a great deal of money in developing an application, it is important that it's protected so that it can not be reverse engineered. There's generally been a lack of understanding of encryption and authentication. Often applications are written with very little understanding of the basic techniques involved in encrypting data and authenticating. There's also been poor development environments, but as we'll see, this has been largely replaced by the new environments such as Microsoft Visual Studio. And there's also a lack of thought that goes into the design process to make sure that security is built into it at every stage. So what we have is old programs, and these programs typically have many issues. As we'll see, we're now migrating away from these old programs, which can be defined as legacy applications, towards new and more robust applications. So the major problems that we have with our application software is there's typically a lack of support for different types of hardware. So why is it that an application written for a PC, Windows PC, can't run directly on a mobile phone? So this happens because the code is compiled directly for the architecture and the processor involved. There's been a weak integration with the web and with the internet for many applications, where the actual code and the web code are seen as separate entities. As we'll see later, the new methods are integrating web code with standard code. Along with this, there's been a whole multitude of application languages, development languages, C++, C, Pascal, Modular 2, Java, Delphi, Algo, and so on. So why do we need to stick with the one language? Why can't we write in whatever language is required? Along with this, there's been a general lack of security, and that programs typically do not bother about the security environment in which they run. There's been a poor robustness in applications where programs often crash. The blue screen of death is seen in many applications, and really very few products in the world would be given such a charmed life as software does. Imagine if a car crashed every single day and we had to reboot it. There's also been too much support for legacy code, in that we've generally migrated operating systems and software so as to keep compatibility with previous versions, so that the code itself typically has legacy code. There's also poor integration with different types of databases. If we have an application, it might link to one type of database but might not talk to another type. Why is it not possible to have a common interface to all data types? There's been a lack of sharing between applications, in that modules created for one application should be able to share the code with other applications. Poor runtime checking is a major issue, in that applications typically aren't checked fully before they're actually released. So when they run on a real-time environment, they might crash. And there's also been difficult deployments. Typically applications fill up whole folders with lots of DLLs and any files and exes and so on. Why is it not possible to integrate these things into simple installs that can be run without the need to register components and so on? Software flaws are a major problem and have led to many applications being compromised. The two main types are intentional flaws, and this is where some malicious party has added a trapdoor or a Trojan into the system to allow the intruder into a host. But typically what we have is non-intentional software flaws. These could relate to validation flaws, where the code hasn't checked properly for the valid user input. In the past, this used to happen quite often, where an application required some numbers and a user entered some characters from an alphabet, and it caused the program to crash. There is domain flaws, where data can leak from one application into another. Operating systems themselves are much more isolated these days, so it's seen as a lesser problem. The serialization flaws, where the output from one program leads into the input for another, and this data flow can be compromised or can cause errors, especially where the memory buffer overflows in between the applications. There is authentication flaws, and this is where the user or the process isn't properly authenticated, so that it might be possible for a rogue library or a rogue process to contact a valid application. There is also boundary condition flaws, where the access to a resource isn't actually checked, and of course there are logic flaws within an application. These are typically defined as bugs. For best practice, there are a few different areas that can be defined which try and overcome the problems associated with software. These are based on the ASP.NET Good Practice Guide. A key principle of this is the principle of least privilege. If an application calls up a process, then it is important that the process itself has the minimal amount of privileges required to actually service the application. In this way, we can minimize the amount of damage that a process might do. So it typically stops a child process from running as an administrator. Another key principle with software is to make sure that we have secure defaults, in that if there is a default setting for security, we must make sure that it's a fairly secure default. Along with this, we need to make sure that when an application is released, it is fully tested before we reduce the security level. A key factor, if possible, is to authenticate users at the gateway to the application rather than at the back end. If it's possible to get into the back end, then it might be possible to compromise. So from a resource point of view, it is good to check the user or the resource at the front end. It is also important that we should never trust external systems and always make sure that we do not pass data to them that could be leaked. Along with this, we should never trust user input, and it should be checked before it's actually sent to any back-end operation. This includes checking for the correct number format, strings, and valid characters. If a date is to be entered, then we make sure the date is of the correct format. To protect our code, we need to make sure that we never rely just on obfuscation for our application, and that typically there are people that might want to find out how something works. So to basically just obfuscate isn't actually enough to hide the code. We need to reduce the surface area and certainly handle errors in a graceful way so that the program itself does not exit in an incorrect way. Defense in depth is a key factor in that we need to make sure that we authorize and authenticate at different interfaces and certainly between different modules. Another key principle is to disable any services that we don't actually need. The more services that we have open, the more ports that we have open, the more chance it can be compromised. And along with this, that the weakest link, so the whole system is only as secure as the weakest link. So we need to analyze the complete system and all the elements and understand any weak points and to try and overcome them. We can have the best authentication and encryption possible. If there is one weak link, such as a password for the encryption keys, then that can compromise the whole system. Okay, so it's well known that software has caused many issues in the past. So let's not dwell on what's there just now, and let's look to the future so that we can build secure and authenticated infrastructures for data and users. The problems that we've had in the past include DLL hell, and DLL hell involves having software libraries on a system that applications use, and then it's possible for applications to come along and reinstall these DLLs with different versions or even with malicious versions. So it has always been a difficulty to keep track of the proper versions and to bind applications to the right DLLs. Another problem has been that applications have too often been bound to a certain version of the operating system, such as the problems that were caused between XP and Vista. and will typically not run on older versions of operating systems. We've also seen applications bind themselves very much to the hardware so that we cannot run them on different architectures or on different processors. Applications themselves have also made direct calls to drivers which can affect the operation of the system. If possible, the operating system should handle all driver access. There's also been a great deal of DLL, driver baggage, where new applications install other drivers and other DLLs into the system. Along with this, there's been poor decoupling between applications, and it's often in the past that one application can affect the operation of another. Along with this, software applications typically run directly onto the hardware and thus could affect other running processes at any given time. So what's the future? So just now we have an operating system, typically. We have some software applications and services which run on the operating system, and then they allow these applications to multitask and get access to the hardware. Typically, all these applications and services run locally, and this is defined as a thick client. Also, the applications are compiled directly for the hardware that we're using. The future, though, might be towards having thin clients and intermediate code. In this case, there is no need for an operating system in that we define a framework, software framework, or a runtime environment. Microsoft.NET defines this as a software framework, and Java defines it as a runtime environment. Then what we do is we create programs which are much smaller and which run inside the managed framework and never actually access the hardware directly. Any problems in the code, any security issues can be handled inside the framework. Again, software services can be provided through this runtime environment. Another change is likely to be towards not running local applications, but to run web-based applications. The advantage with this is that the applications are accessed through some form of web browser, which can run on most types of applications and requires very little memory and very little post-processor requirement. Thus, applications themselves run on the web server on some server technology. This is defined as thin clients. Another change is likely to be as hardware becomes more powerful. We can move away from having applications and operating systems connectedly running on the hardware. It is now fast enough that we can have a virtual server. So VMware, virtual PC and so on allow different images of an operating system to be run, each isolated from each other. This allows multiple operating systems to be run on the same operating system and on the same hardware. So an Apple Mac computer could have a virtual server running Windows XP, another one running Linux, and so on. Another major change is that we have typically built security and applications around certain key ports. So the server listens on certain ports, 21 for FTP, 23 Telnet, 25 SMTP, 110. Our security is typically focused around detecting these ports and blocking them. Unfortunately, many applications won't actually work if some or more ports are actually blocked. So the future is likely to take a port which is never blocked or not typically blocked, and that is the magical port 80, which is the web port. And then what we do is we deliver services through this port 80. The problem with this is that firewalls will not be able to detect the actual content and application. So for example, if FTP is banned, then it would be banned on port 21, but if it was tunneled through port 80, then it might be allowed. But more and more applications are going through port 80. Another change that we're seeing is that the user interface is now being decoupled from the actual business logic. So if possible, an application can be split into a business services layer, data services layer, and then a user services layer, which is the user interface. Then applications can be easily developed for different systems by changing the user interface. In this case, we have the same business logic, same data, and then we can bolt on different application interfaces to give us Windows programs, console application, mobile application, and a web application. This is defined as three-tiered architecture and allows us to put much of our code, developed code, into a business layer, possibly which run remotely from a server, so that the user never actually gets access to the core data and business services elements. Okay, so let's look at one future framework, software framework, and that is the Microsoft.NET framework, which is one of the most complete integrated systems ever created. Basically, the .NET framework supports intermediate code. So the code itself is never actually compiled directly for the hardware. When the intermediate code is run on the system, it is then compiled as it is running for the specific hardware. So this allows us to create a program which will run on any type of hardware and architecture as long as it runs within inside the framework. Another major change in .NET is that it is an open system supporting many different types of languages. So .NET has integrated the previous C and C++ languages into C# and VB, VBA and ASP into VB.NET, which gives an alternative between development. But as we'll see, it supports many different languages. Inside the framework, we have our typical application programming interfaces to give us Windows and typical code. We have a robust COM+ model for enterprise applications, and we have the integration of web services and web applications within ASP.NET. Basically, the key elements of the language is that it has a common runtime language, which is similar to the Java virtual machine, in that programs are compiled to an intermediate format, MSIL, which is the Microsoft Intermediate Language. Much of the logic much of the code is actually run from within inside the framework, and the program itself doesn't need many of the main program elements. To overcome the problems of different systems defining different sizes of integers, for example, one computer might say that an integer is 32 bits and another is 64, and when they pass data between themselves, they can have compatibility problems. .NET defines a common type system for all its data types. It has a common class library where the classes and the properties that are defined and the methods are common across all the programming languages. So a method that relates to one programming language is the same name as it is in other ones. A key feature is that .NET is not built on any specific language, and different compilers can be created So it's G#, C#, VB.NET, Delphi, Fortran can be built for the actual compiler. So it breaks away from the requirement to develop in a specific language. So the framework itself sits on the system and is standardized with a certain version. So this is version 1.1.4322, and everyone will have this framework, the same framework, obviously with different localizations. And the framework itself should be standard and will not change. When a new version is released, it is installed into a different place. These are the DLLs that are called from within inside the framework, such as the MS Core Lib, which is a large library that has much of the core .NET components for security systems, file IOs and arrays and so on. So we can see here that much of the code is in this folder and new versions are created. A great advantage is that it's possible to create an application which binds to a specific .NET framework, so that a new framework might come along and might not work with it, but we can be sure that our existing application works with a previous .NET framework version. So basically what we have is that we have the operating system, and it's possible for us to create processes and applications which produce native code. This native code can be seen as managed code. We allow it to happen, but really the migration must be away from this native code, which can cause many problems with memory and with the processes. So applications themselves can run inside the framework and should be isolated from each other, along with processes. These are compiled into our intermediate code. The .NET framework then translates it into the actual requirement for the hardware. So it's a key feature to take the intermediate code and compile it to the machine code or the native code. Along with this, we have a concept called the Global Assembly Cache, and this overcomes the DLL hell that we used to just have one version of a DLL. Now DLLs can be put into this Global Assembly Cache with different versions. We can see here 1.1, 1.2 and 2.0, and then applications themselves can bind themselves to whichever version they have actually been defined to bind to. Also, we can say that an application could bind to the most recent if we wanted, but the Global Assembly Cache will properly identify the DLLs in the cache and store them. This is an example of our assembly cache. We can see here there is a version number, there is a public key to authenticate and identify this is known as a strong name. These are known as strong names, and properly identify a unique instance of a DLL. We can actually see an example of this, hopefully, looking at our assembly cache here, and there's an example on our system here. So we can see here that we have different versions of different components. Each one can exist. So we have Office Access version 11, Office Access version 12, and so on. We have our key that we'll see in a little minute. So when applications require these DLLs, they will go to the Global Assembly Cache. So the great advantage with .NET is that we can create any type of application we need. Windows applications, web services, and so on. Mobile applications using .NET, which is becoming more popular, Windows services, and console applications. The basic history was that version 1.0 was released in January 2002. With a few little bug fixes by April 2003, we had the version 1.1, which is a classic version that many applications still use. Along with this, a .NET Compact framework, which isn't the full framework but allows mobile applications to work, was released. One of the major steps forward was .NET version 2. This fixed many bugs, it had many new controls, and the major change was ASP.NET components. We could now design web applications which almost had a Windows type look. Along with this, we had serial communications and Bluetooth integrated, which had caused many problems. Another major step was in .NET version 3, which was released in 2006 and introduced 4 new foundation classes: card space for security, presentation, which allows enhanced sharing of data through XML and presentation, communication foundation, and a key element was the Windows Workflow Foundation. So basically we've seen 3 main generations of web development. The first, we had HTML, and we had to find a way to make things more interactive, so JavaScript was integrated into the HTML code. This allowed code to be run inside the HTML and also to react to events. The problem with this is that we were actually sending the JavaScript across to the client, so the client could actually read the code and take the logic from it. The next step was to run the code on the server. So in this way we could take ASP and PHP, and then inside the HTML we added special characters which defined that the server should run the code inside there and convert that into standard HTML, which would be sent to the client. The advantage with this is that no one can see this embedded code. So this was fine, but really it had been extremely difficult to create proper applications which reuse code. So the future is towards code behind, and an example of this is with ASPX files. With this we can have proper events and a proper web page, but it runs code behind the page. So if we see an example of this inside Visual Studio, here is an example. We can just place this over here, and just give me a second. So, okay, so we have our code in a little minute. We have our code, which is our ASPX file. Just slow down a little bit here. We're looking at the wrong thing here, sorry about that. We're looking at a web.config file that we'll see actually in a little minute. So here we have an example of a ASPX file. The source itself looks a bit like HTML and JavaScript and so on. So there's what it looks like as a design. And then what we have is behind that file we have our C# code, which is our code behind. So this allows us to much easier share code. So this code behind this is key for many reasons. So basically where we've been is legacy, and that was the old Windows NT, 98 ME, 3.0, 3.1 and so on. The horrible images of ASP, DirectX wasn't really a very robust system, and the old languages of VB and C++. We're moving into a phase of reduced legacy where we still have some old legacy components, but we're starting to see a move towards these web-based applications and also frameworks and with new object-oriented languages. But the future needs to be without any legacy, and it's only then we'll have applications which will not crash and will be secure. These are likely to be built on XML standards using server-side technologies and with proper frameworks. The major problem that we now have if we use a framework is that we now have intermediate code. The major problem is that any .NET code or Java code can be easily reverse engineered as it is still coupled to the actual source code. So an example of this is that we might have a C# program here, just a little main program, standard application, prints what's your name and then reads it in and displays it. When it is created as an exe and when we view the assembly, an application is called an assembly inside .NET. We can see here that the assembly language that's produced actually still has all the main details of the program. Even the classes and the names in the strings can be easily identified. So it is a fairly simple task to be able to reverse engineer this. So it's important that if we have code, we need to make sure that it's secure and it can't be reverse engineered. So an example of this is that we might take a program, we compile it, and we'll just have a look at that in a minute. Okay, so here we have a simple program, simple.cs. This is a program to determine the square root of a value. So what we'll do is we'll use the C# compiler, simple.cs. Oops. Fortunately, it's crashed. Oops, got the wrong one. Just give me a second. Here we have. Sorry, this is running it through the command prompt here. So same place, we just have a look and we have our program, and then we compile our program, and we see now that we have an exe called simple.exe. Run the program and it should work. Okay, so we have our exe here. So what we'll do is that we'll have a look at that exe. So I have a program called .NET Reflector, and what we'll do is open up the docs source simple, and then we have our exe here. And if we look at it, here is our assembly. Let me just check. Simple.exe. Set it in the wrong place. And it's simple and then in test. Sorry, we had the wrong version there. That looked like an obfuscated version. Okay, so we have a look now, and we can see here that our program itself actually still has much of the code already in it, and we can actually see most of the code already there. So it's a challenge to be able to obfuscate this. So we can see an example of this. Now, exemplar is one program which can take the exe and then convert it back into a CS file. So I have exemplar on the system, and what we'll do is that we'll take the exe and we'll call it list.cs. So we now have a file list.cs, and we can see here that the original program has been restored back as it was. Okay, so exemplar is one example of a reverse package, and you can see here that the original code comes back again. So we've seen in the .NET Reflector that we can actually view the code. There are many decompilers around for .NET and Java. One is the .NET decompiler. So how do we keep our applications and our code secure? One method is called obfuscation. And with obfuscation we try to scramble the application to make sure that it can not be reverse engineered. In this case we have a C program which will actually run, and it is very difficult to see what the output actually is. Unbelievably, the output it prints is the 12 days of Christmas. And it's done this by eliminating white space, uses conditional and list expressions rather than the if-then statements. It has some basic encoding, and it also has multiple functions into a single function. So it's one of our tasks to make sure that we obfuscate our code so that it can be scrambled and cannot be reverse engineered. One method that is used is called identifier renaming. So in this case we take our assembly, and if we run it through the obfuscator takes names, printing names, and will generate, in this case, non-printing characters which are difficult to be able to reverse engineer into the original names. So somebody might be able to reverse engineer the program, but it will be almost unusable because they don't have the original variable names there. We have string encryption. Many crackers work by searching for keywords. A string encryption obfuscator will obfuscate various strings by calling up encryption methods. There is flow obfuscation, and that's where the actual flow is scrambled in some way to hide its actual operation. So there are two examples that you can try online if you require, here and here, in terms of the obfuscator. If we take our simple example again, so our simple.exe has been reverse engineered. So we'll just get rid of the list file, and what we have is that I've got an obfuscator here. So I'll run the obfuscator on the exe. So now we have a new simple.exe. Just check the date and the time. So we have our new simple.exe, just to make sure that it actually works. That's fine. But we should find that when we run exemplar now, it should crash the program. And we can see here that a lot of the strings have been, the identifiers have been renamed. So here's an example. So we can see here, this was our original code. In this example, we have the variable names are still in there, and all the strings. When we obfuscate, we can see here that the obfuscator has changed name into v_0, and it's changed the class name class 1 into A. And hopefully when we run the reverse engineering program, it will show an error and crash the system. Security has been extremely difficult to actually define and get right. And typically the problem that we have is because our security is related to the attributes of files and data in operating system. That is what typically defines the security of any entity. An improved approach and a more simplistic approach is to go for role-based security. And role-based security defines roles that an individual or entity can have. With this, we have IDs. In this case, we have Bob and Alice, but we also have roles. So in this case, Bob might be part of admin, along with Carol, and then Alice here has an ID, but she is part of guess. We simplify the security by defining the security applying to certain roles. The roles typically relate to the organizational infrastructure. So in this case, in a non-role based approach, it is the operating system which defines on the roles themselves. The application itself takes no judgment on the IDs and roles and will generally just run in the same way. Unfortunately, this is divorcing the requirement for security away from the application into the operating system. An improved approach is to integrate the application or a web application with role-based security, and with this the application directly integrates with roles and with IDs. So the authentication could come from Windows login, basic username and password. A passport type authentication might be from Microsoft Live site. Form-based, Windows-based built-in, where it's the user login here, and this is from a web form. And we might also have the web server authentication. So more and more applications will actually have security built into them at the core, so that it is not possible for users to access certain parts of the application. In our .NET application, we can have direct access to these roles if we add in the principal, the system security principal namespace and security. And for this, we can find out what the ID of someone is, and then we can find out what type of authentication they're using, and then what their role is. In this case, are they an administrator? If they are an administrator, then it can print this line. If they're not, then it prints this line. So in a .NET application, we can integrate security in the form of IDs or roles. Some of the IDs that we have is it an anonymous user? Has it been authenticated? Is it a guest? Is it a system account? And obviously we can check its name. We can also get its authentication type. Some of the standard roles that we might have in an application are administrator roles, guest, power users, user, and so on. So we can check each of these so that we can actually stop or allow users and roles into certain parts of an application. So what's the model that .NET applies? Basically, we have what's called a strong name, and strong name gives us cryptography to be able to uniquely identify a DLL on the system. And no two DLLs should have the same version and public key token, and it overcomes DLL hell. Basically, a strong name is defined. It has its text name, its version number, a public key, and a basic digital certificate. And with this, we can actually sign DLLs to make sure that we can validate them when we use their public key. If we use their public key, then we can actually find out that it has been signed with an organizational private key. To create this, we can use the SN-K, and that creates a key pair, the public key and the private key. We can see here we have our key pair. This is then added into the application, and we can see here we have our public keys, which should be able to authenticate our DLL, and it's integrated into an application above the method that it's, or the namespace that it's related to. So let's look at the general .NET security model. Basically, it tries to keep things fairly simple in that the configuration files themselves are stored in an XML format. It is important that these files are kept in the correct format, as the machine can stop operating if they're incorrectly set. Basically, we can define an enterprise policy, and that relates to all the machines inside an enterprise. We can have a host policy, and then a machine policy, and then a specific host policy. Basically, there are three main configuration files that are actually set. There's the general machine configuration, which defines how the machine works and how the security is defined for it. Each application can have their own configuration file, which defines the security of it. For web applications, we have web.config, and for normal applications, we have app.config. And then there are various security configuration files, such as for the enterprise, the machine, and for the specific user on the machine. Each one of these tends to inherit from the one above. This is the highest level security, or the minimum security, higher security, and then the user security. So the basic policies that we have are enterprise policy, machine policy, and a user policy. The user policy itself is typically stored on a local folder. Because this is so important, and if we make an incorrect update, then it might change the operation of the machine. The configuration files are typically stored in multiple versions, so that we can backtrack from one to another. If we have a look at the configuration on a machine, we can see enterprise, machine, and user. It's possible for us to look at some of these files, hopefully. Okay, so that's what the security.config file has in it, and it defines basically the security settings for a specific user. For the machine, it is stored inside the .NET Framework folder. What we'll do is we'll have a look at that first, and hopefully we should be able to see different versions of this. So in here we have security.config and enterprise sec. So we'll have a look at this is different versions here, and we'll have a look at this one. So this shows us a security file. So these are key configuration files that we have on our machine. So the previous example showed the .NET framework. The big move towards the future is likely to be towards ASP.NET, which gives us a web infrastructure and a possible move towards web-based applications and thin clients with a highly secure infrastructure. Basically with ASP.NET we have a web.config file, and each web page inside a certain folder reads the web.config file and then inherits their security from it. So an example here is that we can say for the authorization we can deny users, or for the authentication we can define that we are using a form for the access to a web page. In this case we're using forms. We call up a login.aspx page, and then the credentials that we have, the only users that will be allowed access to these web pages inside that folder are the users who give their username of Fred, Bert or Napier. So we'll have a look at this. If we just get rid of what we had before. Okay, so we've defined, this is the web.config inside this folder. Here it is down here. And we defined that the authentication is with forms, and these are the users that are allowed access to the pages. So if we set this page to be our startup page, what should happen is that when we run this, we should not be able to access this page unless we've actually authenticated ourselves onto the system. So you can see straight away it tries to call up that page, and it just takes a little minute because it's running locally on this server. We shouldn't be able to access the page, hopefully once it displays. It just takes a little minute. It doesn't usually take this long on a real server. It's because we are simulating it. And it should load. Okay, so we haven't been allowed to get access. If we try any username and password, it shouldn't allow us in. Again, this would be done fairly quickly on a real server. What we have is a simulated server here. Now we define Fred with a password of pass1. And this time we should be able to be authenticated in. So the web.config is storing our security settings for our web pages, and in there we can define different forms, who's allowed to access a form, a certain user, how they're authenticated, and possibly what their usernames and passwords actually are. This gives us a single point of configuration. So we can see here we've managed to get into this page now because we authenticated ourselves properly. And it's through this web.config file that we can keep secure. Okay, so it's possible for us to take that out. And now we can access the page directly. Just put it back in. Oops. Okay, so the web.config file is becoming more and more important and is the place that we can refine our security. We can also define if there's a debug. If a page crashes, we can define whether it shows debug information. Often in a production environment, we don't actually want to show any debug information because it can show some of the details of the code behind it. So what happens if we try to access that web.config, because we could actually see what the security is? Luckily, it gives us a server application and that we can't actually access it. So no one should be able to access the web.config file. So one possible infrastructure for the future is to have a web server interface for clients built on IIS, typically version 6 and on, with ASP.NET. Behind that we can have IIS ASP.NET, which gives us web services. We can also have .NET Remoting, which allows us to run remote applications, and for robust enterprise solutions we can have a COM+ level. And then as a backend we can have the robust database server of SQL. Some of the forms of authentication for IIS include anonymous, basic, digest, integrated and certificates. And for authorization we can use NTFS permissions from the file system, IP restrictions. For authentication, as we've seen, we could use Windows itself to authenticate the user. We can have forms, as we've seen, passwords, and none at all. And then for authorization, we can have URL authorization and file authorization, along with what, as we've seen, .NET role authorization. So ASP.NET is built on a very strong foundation based around these robust components. Basically what we have is that we can have the client himself, and the client himself has got to run things on the web server. So typically what happens is that an impersonation is defined. So the client itself is transformed into a impersonation, and then that impersonation is allowed access to the local resource. So we can see here that the impersonation is IIS iUsers, and you can see it has limited access. It can't modify or control anything on the local resource. So this is defined in the web.config as impersonate equals true. Along with this, if there is something on another server or another site, we have delegation. In this case, it might be the web server here and a database server over there. There is now a delegation of the client to another entity to access the remote resource. Again, this should be the minimum security level required to access the remote source. To stop spoofing and covering of trails, only one hop is typically defined for delegation, so that multiple hops cannot be used. To show the whole complexity of the .NET infrastructure and the possible roadmap of the future, we can see here a typical type of infrastructure. This shows the browser, and then we have our ASPX requests over the internet to our IIS server, which is running ASP.NET. Behind it we can have enhanced services such as Windows SharePoint, which allows us to create web pages, create web parts for forms, and that integrates with an Exchange server to be able to send email, and also with a domain server which defines the roles. Behind this we have our ASP.NET forms, and then the Office SharePoint 2000 server, and this gives us access to Excel, InfoPath, Project, and so on. Behind that we have our basic client applications such as Visio, Access, Word, and so on. And then to be able to develop for this, we have our development tools such as Visual Studio 2005 and 2008, which are built on these technologies, as we've seen, and which allows us to build robust communications and infrastructures. We have an SQL backbone here. So this is possibly one of the architectures for the future for information delivery. So overall, we've looked at many different areas, including some of the problems in software, and then looked at how the .NET framework could actually solve many of the problems and could provide us with a roadmap. It is not the only framework, but it is a usable one, and is one that has been well tested and is now growing in popularity. We then advanced onto ASP.NET and showed how we could create a web infrastructure and also integrate security with role-based security and having files such as web.config. And then finally we looked at a possible infrastructure using the .NET Microsoft SharePoint server.